Hi, I'm Masai, and I will talk about FaceCommands, user-defined facial gestures for smart glasses. This is joint work with Kai Sensei, Sakamoto Sensei, Sugiura Sensei, and Sugimoto Sensei. And let me start by use cases. Imagine that the user is at home and it is a smart home, so the appliances are connected to the internet. They can be controlled remotely. Now the user is wearing an optical see-through display such as Google Glasses or HoloLens, and this is the user's viewpoint. And now the user stared at the ceiling light for a short moment, and the optical see-through display recognized it. Then some information popped out and indicating the action the user can take for the light. And the user wanted to go to sleep, so they made the eye closing gestures. Then the display recognized the gesture and gave a command to the light, and the light is turned off. And user took off the display and went to sleep. And in the scenario, the user made the eye closing gesture to turn off the light. And our work investigated how to make this scenario realistic by conducting two studies. The first one is the elicitation study. How can we design the face-related gestures to perform specific tasks? In this case, control smart home appliances. And we report the analysis and takeaway messages. Second, a feasibility study. How can we recognize face-related gestures using sensing modality that can be potentially integrated into optical see-through display? So let me talk first about the elicitation study. And as we see more and more augmented reality applications from research being applied in everyday life, we can assume a large adaptation of optical see-through display in our life. However, there are problems with the existing input methods. And additional devices are limited when hands are full, and the interaction on HMD has a limited area. And mid-air gestures require space and may lead to muscle fatigue. And considering this situation, we believe facial gestures can be an additional or alternative means. Facial muscles can be controlled intentionally and allow hands-free and subtle, silent, and intuitive interaction. We use the term of face-related gestures from now on, which we mean any gestures that involve the movement of facial muscles, eyes, or heads, or the combination of those movements. And we took a user-defined approach for designing face-related gestures. And this approach employed users in the design of gestures. It showed that our participants are computational effect to be caused by using a gesture, such as turning up the volume, and ask them to create a sign that activates the effect. And according to Morris et al., a gesture set designed by this approach is preferred to the one by human-computer interaction researchers. And user-defined design is now a standard method and applied in a wide range of domains, such as mobile tasks, smartwatches, and augmented reality. And a gesture set for HMD interaction is also explored with this approach, mostly for head gestures and hand-to-face inputs. However, there's little research about a whole face-related gestures design, and we want to investigate which face-related gestures are good for a specific task and which part of the face is usable as an input gesture. And what do we need to consider when designing such gestures? So we conducted an elicitation study using the online crowdsourcing service, Amazon Mechanical Turk. It aims to include a broader user base. And first, we conducted an exploratory study, and we found it difficult to design user-defined face-related gestures. So we made a design reference to make it easier for the participant to design gestures. And we selected 15 daily mobile tasks considering smart home context based on previous studies. We showed a picture or video of each task to constrain the associated image. And all of them were answered by text using Google Form. We had valid proposals from 37 participants, and the proposal gestures are coded into action unit-based group manually by an experimenter. So the result, while the distribution is different depending on the tasks, the participants proposed facial gestures most frequently overall. And positive or high arousal gestures, such as lifting eyebrows, smile, and so on, are included in the study actions, such as turning on a TV or the play music. And based on the comments, we summarized the pros and cons of face-related gestures. And the advantages are the accessibility and usability. So face-related gestures can be used by people who can't speak, and they are hands-free, easy, fast, and silent. So they can fit multitasking. On the other hand, some participants were concerned about the misinteraction by natural expressions. And some argued that eye gestures should not be used when visual attention is needed, such as driving. Also, some are concerned about running costs, such as memorability and adaptation. This means that at first, the face-related gestures could be used as additional means to existing technology, such as voice commands. And facial gestures are acceptable to the users, as is the use of head and eye movement. Simple gestures are preferable in daily life than complex gestures. However, this leaves room for misinteraction and potential high false positive recognition. And socially unnatural behavior like yawning should be avoided. and metaphors associated with tasks are essential to consider when designing face-related gestures. And use positive or high arousal gestures as a trigger to calm devices. Eye gestures are good to show the task direction, and lifting eyebrows works as a metaphor for initializing a communication, and a wink can be a metaphor for the shutter release button of the camera. And paired gestures should be used for paired tasks, such as turning on and off the light. So these are the takeaway messages. And we designed the gesture set based on them and scores that calculated from proposal ratio. And this score is a bit different from the normal agreement score to consider a bias for suggesting gestures that are easy to come up, which was more evident in Mechanical Turk. Sometimes we added a second option to consider gesture conflicts, coherence in paired tasks, and the two highest scores. So these are the results: so making a call by smile, or turning a TV by lifting eyebrows. So now we designed the face-related gestures, and let's move on to the feasibility study. So many pieces of research demonstrate the technology to recognize head gestures, eye gestures, and facial gestures. And for wearable solution, earphone type and eyewear type are two major form factors, and we focus on eyewear type to consider potential integration for optical see-through display. And various sensors such as optical sensors, EOG, EMG, capacitive sensors are used for the recognition. And we choose the optical sensors as it is a low-cost and contactless sensing. And this allows classifying eye gestures and facial expressions from skin deformation caused by the facial muscle activities. And we designed the hardware and software. And please refer to the paper for the technical details. And the improvements from the previous research of using this device are the first, we added the IMU 9-axis sensor to compensate for head motion noise. And second, our method used the convolutional neural network to detect the time series gestures. We can detect facial gestures and eye gestures at the same time. And also, our method can robustly recognize deliberate gestures as the algorithm considers the time series. So we ran the technical evaluation to show how well technology can recognize face-related gestures. The target gestures are 8 kinds of gestures from the gesture set we designed in the Elicitation study. We excluded head-related, as many previous studies already showed its feasibility using IMU. We recruited 13 Asian students in Japan and collected the data. For training data, they made 8 kinds of gestures 20 times based on the software instruction. And also we collected non-gesture data while they moved their heads and kept their heads still. And for test data, the participants made the 8 kinds of gestures 4 times in random order within 90 seconds. This process was repeated 3 times. And so we have this 160 gestures for training data and 96 gestures for test data. And this is an example from the experiment. The user made the gestures at his own pace, and we superimposed the recognized results afterwards. You can see that the technology can correctly recognize the face-related gestures. And we first investigated the accuracy using the trained data only. We did the leave one user out cross-validation. So we trained that with the 12 participants data and tested another participant gesture data. And average accuracy was 61.4%. And most of the errors are that the gesture data was recognized as a non-gesture class. Considering that the random chance level was 11%, and the result was not bad, but there are rooms for improvements. And for user-dependent tuning, we showed higher accuracy of F1 score 8.911, and wink was the easiest to recognize, and opening mouth was difficult as it showed a lot of false positives. Note that we did not count the non-gesture class, as there are many data points compared to other gesture classes. And also the experiment did a more realistic scenario where he made a smile and wink twice every 4 minutes while doing some indoor activities. In the meantime, he watched a comedy that induced some natural smiles, and he walked around in the room and corrected the device's position many times. And the result was good, so there are only one false positive of wink by scratching the nose right side, like this, and F1 score of 0.921 for smile and 0.867 for a wink. And it is very important to reduce the false detection of gestures for realistic scenario while keeping the usability of this technology. And we discussed the 5 topics in the paper, such as improve data quality, use sophisticated algorithm, consider independence of gestures, use a trigger command, and combine the different technology. And for limitation and social implication, we described about 3 topics, such as mechanical Turk noise and algorithm generalization. And please refer to the paper for more details. And we believe the sociological aspect of performing gestures is especially important. Technology may alter the role and usage of facial expressions in human-to-human communication, and we need to consider culture and each user's preference. And this is the summary, and I'd like to end my talk. Thank you for the attention, and I'm happy to take questions.